So you're going to do a senior design, right? Okay. If you're holding any interesting ideas, go ahead to implement that. I would love to see that. Okay, so let's get started. This is our last lecture slide of this entire semester. Okay, so once we finish today's lecture, and we are going to meet on next Monday to discuss the final exam. Even though we actually I can do the discussion today, but it means on Monday we will not see each other. I really want to see you last time on Monday, if that's the last meeting we have between you and me. Okay. All right. So in this lecture, and we actually going to explore how operating systems handles multiple processes running seamlessly at the same time to about how to avoid conflicts. Then they share some data. So previously, we have introduced the concurrency as the core concept, and we now basically deepen our understanding by looking at very specific at a parent or pseudo concurrency. Why pseudo? Now, this is a slide basically introduce that or illustrating that we have one single CPU, has one single core, has one single thread, only one single instruction from one process can execute at any given time. That is the idea. But yet we are having some mechanism called rapid context switching. And the operating system cleverly gives us an illusion of multiple processes running simultaneously. That is why it's called pseudo. And consider our diagram here. We have process P1 and P2, each have their own instructions lined up and waiting for the CPU time. And the CPU quickly alternates between executing instructions from each process. It's very similar to let's say, a chef. A chef is preparing two dishes and simply by quickly switching from one to the other. So neither dish will be cooked simultaneously, yet both dishes progress seamlessly in parallel. So it's kind of like parallel processing. So because of quick switches. So this is exactly what we have here is how apparent concurrency works. Simply remember, the apparent concurrency is simply means there is no true parallel execution happening. It's just a very efficient task switching. So next, we are going to see how the true actual parallelism differs with the multiprocessor system. Here it is. So in this system, with multiple processors or cores or multiple threads, we achieve a genuine parallelism. So multiple processes truly run at the same time. Consider the diagram here. We have multiple states running and waiting and indicating different processes interact simultaneously. For instance, our P1 might be active running on CPU and process P2, the P2 is waiting on IO, P3 is waiting on IO and will be put into ready queue. And simply P2 and P3 are managing its own context and running simultaneously to check if I'm going to moving to the ready or not. Now, the operating system generally having a good control on that. Using our earlier analogy, we have talking about chef. Now, simply imagine multiple chefs are cooking at the same time on their own dishes simultaneously in the same kitchen. So that is a real parallelism executions. This scenarios create some more new challenges as we talk about in previously even in apparent or pseudo parallelism, you still have such problem, but this problem is more serious. So when a process is run simultaneously, they may access a shared resources concurrently, leading to the potential risk conditions. Synchronizations now becomes very essential to ensure the data integrity. So with this fundamental distinction clear, we know what is pseudo concurrency and what is true concurrency. Now we're simply switching to what exactly the problem they are bringing us. Okay, now let's examine the practical challenges introduced by concurrency. Whether it's pseudo or true, we are all having this problem, focusing on the shared data. So in multi-programming system, the CPU rapidly switches between multiple processes, allow them to progress seamlessly at the same time. So user commonly share the data across those processes, at which operating system must handle them carefully to maintain the data integrity. So let's consider this very simple scenario or simple examples. Two concurrent processes, P1 and P2, both updating a shared variable x, initially set to be 4, as you can see here. The P1 intends to add 10, P2 intends to add 2, running sequentially. We will eventually get one number. 4 plus 10 plus 2 is what? Yeah, just quickly doing the math, quickly waking up your brain is 16. Eventually, whatever the order we are doing, eventually we will get 16 as a result in a sequential order. And however, in a concurrent execution, unexpected result may occur if the context switching interrupt in the middle of the process. Big disclaimer, what we have here is we are talking about pseudo concurrency. Its problem will be enlarged in a true concurrency. So let's talk about simple scenario first, then coming to the true scenario, which you can consider on by yourself. But here in the class, we are only focusing on one CPU, one core, one thread for this illustration. Now, simply analyze this, how concurrency leads to unexpected result by, so what do we have here? So first, consider an interleaved execution, what we have discussed. P1, beginning with loading X initially, compute 4 plus 10, which temporarily holding that value of 14. We haven't write to the disk, so it's still holding that information. However, before P1 can actually store that result, a timer interrupt occurs, saving that P1 state into its PCB. Now P2 simply runs completely, loading X. What is the current X is? What? 4. 4, still 4. Adding 2, which is value of 6, back into the memory. And when P1 resumes, it still holds 14 as a result. So from its earlier computations, now it simply overrides the 6 by setting up by the P2 and simply overrides that, it will become 14 as a result. So the value of X becomes 14, clearly shows some data inconsistency. It could be 6, could be 14, who knows that? Okay. Now, simply we contrast the scenario, the sequential scenario. Suppose we have P1 entirely running first, loading that information, adding 10, and sort back to X. And now X is loaded, which is loading, basically loading 14 now, and we add 2, which is 16. Okay, that is the idea what we have. Now, we have actually want to illustrate what is happening in the concurrency, what is the underneath mechanism behind those like concurrency risk conditions, what is exactly happening. So simply visualize this step by step. So what we have here is a shared variable, and both processes can access the variable. So currently it's holding 4. Now P1 is running. We're simply loading that information into its working bench. The working bench, what we're talking about is loading that information from the disk to the memory and to the register. Register is our working place. Now it's loading that information 4 into our working place register. Next is we do the computation. X is equal to X plus 10, which is 14. Now, the problem is coming. Timer interrupt. We have known that. Timer interrupt kick in. It means, we have to store this information back to P1's PCB. instead of completing our full execution, store that information back to X. So it's have to loading that or store that information back to the PCB. PCB1 is having the 14, okay? Now we are quickly switching the context to P2. So P2 is now doing the execution. It's still loading the information of 4 into its register and doing the computation and writing that computate result back to X, storing that back to the memory. Okay, now we have the memory of X is holding 6. Now we are actually assigned, CPU is assigned to P1 again. P2 has finished its job. P1 is now in execution. What is the information is loading from? It's loading from PCB. Now PCB is holding that 14 and loaded to the register again. Now it has a final step to complete, writing that information back to the X. Now X value has been changed to 14. What you are seeing here is a scenario as clearly illustrating the concurrency issue known as race condition. That is the race condition we are talking about. So from the scenario we just worked through, it's just seeing a firsthand of how concurrency can cause inconsistency. Specifically, we'll observe the 2 different values, 6 and 14, then for the shared data X due to the uncontrolled concurrent access. This problematic scenario is not formally called race condition. It occurs precisely when multiple processes access and modify the shared data without proper synchronization methods, leading to unpredictable and erroneous outcomes. But how we can define that? We have to understand the scenario, but we need to define race condition. By definitions, a race condition occurs when 2 or more operations manipulate shared data concurrently, and the final outcome depends entirely on the order in which those operations happen. So this is undesirable because the ordering is not in our control. It's not under the control. The scheduler decides which process runs. To avoid this, we must ensure one process at a time to have the exclusive access to the shared data while modifying the data. So the requirement is called mutual exclusion. When one process is inside its critical sections, no other process should be allowed to enter the same section. So achieving this mutual exclusion requires some kind of form of synchronization mechanism, a structured way for processes to coordinate the access. So most operating systems rely on some kind of representation of lock, either by a simple lock byte or semaphore or another physical or software construct that signals the ownership of the resources. So with those principles in mind, we now can look at a very practical mechanism that implement mutual exclusion safely, which is the low-level atomic operations. So we just identified the issue with race conditions. We formalized the concept of critical sections, and we have mentioned the critical section. What exactly critical section is? That's none by definition here. The critical section is basically the portion of the code where shared resources like variables, files are accessed or modified. To ensure the consistency, only one process should execute its critical sections at a time. This principle is known as mutual exclusion. Now, we formally define 2 terms, critical section and mutual exclusion. Any robust solutions to managing the critical sections must satisfy 2 conditions, mutual exclusion and progress. Now, another different terms. We have understand mutual exclusion, but let me to simply illustrate or emphasize that. Mutual exclusions ensures no 2 processes are ever simultaneously in their own critical sections. That is one. Progress guarantee that when no process is currently in the critical section and others want to access, the system efficiently decide which process can enter next, preventing unnecessary waiting or deadlocks. Okay, one is we don't have risk condition happen. The next part is we don't have deadlock happens. Okay, that's two terms. Next, we are going to look at very specific synchronization tools that help us to enforce those conditions in practice. So we simply examined a very straightforward technician or synchronization technique, which is called test and set. So which is designed to enforce the mutual exclusion. The principle is very simple. So before we enter the critical sections, and we call critical section as CS, this is the critical section. A process must successfully perform a lock operations. When this done, it's executing the unlock operations. On this slide, what we can see here is two processes, P1 and P2, both attempting to enter their critical sections by using lock X and unlock X, as you can see. And the key point here is if one process obtains the lock, the other must wait, ensuring the mutual exclusion or preventing the risk condition. Simply, let's use an analogy to represent. I think it is a more obvious way to understand this. Think about the critical section as a one-person restroom, okay? To avoid the issue, the wrong risk condition, we use a lock on the restroom door. So lock the door, if the P1 enters, it locks the door. That is our lock operation. No one else can enter that room until P1 done its job. Then coming with P2, seeing that door locked, if it has some kind of indicator of seeing that, but doesn't have the indicator of what is happening. P2 will consistently trying that door to see if it's locked or not unlocked. So simply that is the thing the P2 is doing. So P2 can, if P1 finishes its job, P1 exit, unlock the door, exit. Now P2 can enter and lock the door. That's the idea. This simple idea ensures mutual exclusion, allowing one process in its critical sections at a time. Now, practically implementing this lock and unlock operations we just talked about, it will be done in high-level instructions. That is test and set. This involves very special Boolean variables. Here we denote as TS. It's Boolean. Boolean means 0 or 1. Okay, which initially is set to be 0. So the lock operation will continuously checking the TS. If the TS is already being 1, it means it's locked. And the process loops simply repeatedly testing the variable's value, a condition known as busy waiting. Okay, now only when PS becomes 0 unlocked does the process set to the TS to be 1 and enter its critical sections. Upon the completion, the process resets the TS back to 0 with unlock operations. Now, you have heard me about this example, heard me about analogies. What is kind of drawback you have seen? You can know this. What is drawback about this process? Yes. Takes more time. Why it takes more time? You don't know? Any other answers for that? Yes. Then the other one cannot access that one, so you have to wait. Yeah, that is the idea of this. But what is the drawback? Do you have to state? Yes. Based on, I don't think that this class, should be the problem is resolution of the problem. Other things that they consider a lot of the process which have to show the process. Is it? Any other idea? Yes? Mm-hmm. Waiting. Okay, so how the drawback actually for this method is the processing resources. The process waiting to enter the critical section will consume the CPU cycles. It has to run on CPU to check on the door consistently. It is waiting on that time. If we're only having one CPU, it means whenever we context switching, the P1 is still doing a job and P2 consistently checking on the door, checking on the door is locked or not. So that's efficiency known as busy waiting, wasting the valuable processing time. And just think about our restroom analogy, okay? It means you enter the room and you are doing the job, lock the door. Somebody else coming to, and there's no indicator. It only knows the door is something closed, but it's never knowing the status of the lock. You have to consistently checking. Is it locked? Is it locked? So I want to enter. Is it locked? And you are being annoyed by this kind of motion. See, that's the thing. You are being annoyed. P1 is doing the job, and entire operating system is monitoring the restroom, is seeing somebody else is consistently making noise and consistently wasting your attention to the other progress. Okay, that is thing that this repetition of checking and checking the lock is busy waiting, and it is inefficient because it consumes unnecessary effort. Operating system is monitoring this, and in operating system or in our computer science terms, it is CPU cycles, is wasting the CPU cycles. To overcome this inefficiency, so the better approach would be something akin to some kind of form of line or queue, that is thing where the process waiting without consistently checking. So this leads to a more natural, a more efficient synchronization method, which is called semaphore. So this is a more efficient mechanism. A semaphore is essentially an integer value, which simply call, let's say, S. Access only through about two atomic operations. One is called wait, one is called signal. Think about the semaphore as a signaling mechanisms of managing the access. Now you're probably having a indicator at the restroom. Simply is saying, it's locked. You don't have to knock on the door. You can see the light is red. So it is being locked. And when the process attempts the waiting operations, it's simply going to check the semaphore value. Simply look at the light. And if it's positive, it means it's green, and it proceed and reduce that value by 1, and then that semaphore value is 0 or negative, and indicating the resource is already in use, and the process locks itself. And the operating system moves the process if it is blocked by itself. It's looking at the red light, it's blocking by itself. The operating system then moves that process into a waiting queue. So will patiently sit right there, don't move until that person is finishing his job. Okay, you don't have to lock it. You have to check it. Look at the light. I'm asking you to sit. Okay. Now it's basically ensuring the efficient resource management without wasting the CPU cycles throughout the busy waiting. So once another process releases the resources and using the signal operations, what we have is signal operations, the waiting process is unblocked and can be proceed. Then operating system will automatically allow you to proceed. You don't have to do that. You don't have to do this consistent checking. Okay, so now you have understand the waiting, the signaling, and everything by using an analogy. We have a more concrete, robust way to understand that. But how is doing that, and why it can do that? That is coming from the implementation itself. So before we're talking about implementation, we have to talk about history. So why is, the waiting is calling P, why is signal is coming is calling V. So historically, semaphore operations are initially labeled with simply letters. P stands for waiting, and it is the language. Can you guess the language is it? It's definitely not from English, right? Never know that. German? Nah. Dutch. Okay, it's Dutch. So I cannot pronounce that, but it spells as Proberen. That's a Dutch word. So it's meaning for testing. And V is also from the Dutch and something spelled as Verhogen. So meaning to increment. So this each semaphore also maintains a waiting queue, as you can see here, the waiting queue, and to manage the blocked process orderly. And just like the waiting line outside our restroom, we have talked about it. Now, how we are looking at the pseudocode of P and V. So both operations must execute atomically, meaning no interrupts can occur during their execution to maintain consistently. Now, I have introduced the atomic operations. Before this lecture, what is your understanding towards atomic? Anybody? That is from the physics. Yeah. So atomic operations. What is exactly atomic operation? I believe this is a very basic education you should receive, atomic operations. What's that? A bomb? Any other things? So you never know about atomic operations? Oh my God. Okay, so now you know that atomic operations, whenever a person is mentioning this function should be doing some atomic operations, it means no interrupts can alter or occur during their execution to maintain consistency. No interrupts. Simply, it means whenever you are doing your job, you are building a wall around you. Nobody can interrupt your action. Okay, that is what we call atomic operations. All right. But next time you're just not mentioning, oh, it's a bomb. Oh, it's not a bomb. Okay, so now coming to what we have here is in the wait operations, the semaphore value is decremented by 1, as you can see. If the result becomes negative, the process is blocked and added to the semaphore queue. That is what we have here. Conversely, we'll have signal operations, which increments the semaphore value by 1. And if the value is 0 or negative, it means that the process is still waiting, and the operation then removes one process from the waiting queue and placed into the ready queue. We have understood the waiting and ready already the state in our previous lectures. Now, but how we can do that, how we can ensure the semaphore operations executing correctly, they must be atomic. Okay, it's not bomb. It's meaning no interruptions should occur in mid-operations. What we have here is introducing or more concept to our PSW. So previously we have the interrupt flag, the mod, the IP, everything is being touched, but we have not mentioned one thing, mask. Now we are filling the gap, the mask. The miss is called this slide simply introducing the concept of masking interrupts, which temporarily disables interrupts during the execution of critical semaphore operations, P and V. So the reason of this is straightforward. If the interrupt were allowed during the semaphore operations, the context switching might occur at a critical time, critical moment, causing an inconsistent state or race conditions. So here we see an example using process state word PSW. A mask field within the PSW controls the interrupt are permitted. And for instance, we are setting the mask is equal to 0 for the timer interrupt TI. And it means the interrupt is currently blocked or masked. Therefore, the CPU is using semaphore operations or instructions without the preemptions, preserving the atomically needed for managing the concurrency safely. All right. Now, let's very clearly focus on how processors using the semaphore operations to enforce the mutual exclusions. Consider we have two processes, P1 and P2, and we're each waiting to access their critical section, CS. Both processes follow a very similar pattern. First, we are calling PS, P of S, and attempting to require or acquire the semaphore. If successful, they enter the critical sections. After the completion of critical sections, we call VS to release the semaphore. Which says we previously discussed those PS and the VS, which simply don't repeat here. What I want to emphasize on this slide is those semaphore operations provide a very structured way of managing the mutual exclusion. At any given time, exactly one process holds that semaphore and access the critical sections, while others will simply waiting patiently, efficiently in the semaphore queue. Thus, the semaphore implement mutual exclusion cleanly, effectively preventing the race condition. But how is Dante doing that? Is what we have here, step-by-step execution. So we begin with the process P1. Just think about it. Process P1 to enter its critical sections. Initially, semaphore S has the value of 1. We have a value of 1 here, that indicating what that critical section is currently free and ready to be entered. At this moment, P1 is executing the semaphore operation, P of S, PS, simply attempting and decrementing semaphore value and acquire the access. As you can see here, the value of the semaphore is being successfully being decremented from 1 to 0 by indicating that critical section is now being occupied. P1 thus enter its critical section. Simply notice the value here. No other process can immediately enter. While P1 is executing its critical sections, a timer interrupt occurs. It means somebody is doing the context switching. This will be temporarily moving the P1 from the running state back into the ready state, ready queue. However, the more importantly, to recognize that P1 is still holding that semaphore. The critical section remains occupied, even though P1 is momentarily paused. So now P2 attempts to enter the critical sections and executing the semaphore operation, P of S. Simply remember, the semaphore value is currently 0, and which means the critical section is occupied. Therefore, P2's attempt to enter that immediately will be not successful and will lead to a different outcome. As you can see here, P2 executing P of S is still doing that job, but once it's doing that P of S, the semaphore value is decremented again. This time becomes -1. So negative semaphore means the process are waiting. You need to wait. The critical section is occupied and no additional process can proceed until the current one release that semaphore. So since the semaphore's value becomes negative, P2 is blocked. And as you can see, its PCB is removed from the running state and placed into the semaphore's waiting queue. So this is a very clear way to illustrating how semaphore operations efficiently handle the waiting process. No unnecessary CPU cycles are wasted. And now, next, the CPU is simply reassigned back to P1, allowing to continue execution within its critical section. Simply notice how the system prioritizing completing the critical sections for the process holding that semaphore, ensuring the mutual exclusion and consistent resource use. And the next one, we have P1. It has finished its critical sections and now executing the semaphore operations, V of S, basically incrementing the semaphore value. And just simply remember, this incrementing action will signaling the critical section is now available again, potentially waking up any waiting processes. Now, the semaphore is critically increment from -1 to 0 by P1 of VS, P1's VS operations, and 0 value indicating that no process occupying the critical section, but the processes may still be queued. This increment simply serves as a notification to the waiting queue, to waiting process. So they can now attempt to enter next. So that is simply a signal. Now, P2 is previously blocked here and putting the waiting queue, are now waken up and moving to the ready queue. As you can see here, the semaphore value incremented by P1 is now at 0, indicating the critical section is available. Thus, P2 can attempt to reacquire the semaphore and enter the critical sections at this time, and mutual exclusion continues to be preserved efficiently. Okay, now what we have here, observing that P1 remains running while the P2 is staying in the ready queue and for its turn, simply waiting on its turn. Now, the semaphore value is 0, and it clearly indicating the mutual exclusion is enforced, and this step simply emphasizes that the semaphore operations ensured orderly access, okay? Now, last 2 slides. What we have here is further illustrating the semaphore usage. So simply consider a bound buffer procedure or producer-consumer scenario, which is a classic example from multimedia systems. So we have 2 processes. P1 is acting as a producer and P2 is acting as consumer. And P1 is reading the data from the network connection and stores it temporarily in a buffer, as you can see. Well, the P2 is serves as the consumer. It reads the data from this buffer and sends it to a, for example, radio or video, audio, some hardware. And notice clearly that both P1 and P2 uses some semaphore operations around these critical sections, effectively coordinating access to the shared buffer and ensuring that smooth data transfer without conflicts. Now, here it is. So we simply look at the sequence of each processes. Simply, producer is now first producing the item. Now it is going to call P of full to ensure the buffer isn't full. And P mutex is simply checking for the mutual exclusion before inserting an item into the buffer. And after the insertion, it will cause V of mutex, simply release that mutual exclusion, and the V empty is to indicating the buffer is now empty right now. So conversely, in the consumer side, it will cause P of empty to ensure something is there that I can consume. And P of mutex, it simply means for the mutual exclusion. It retrieves that item and then calls P V of mutex to exit the mutual exclusion. And P V of 4 is simply shows the space is available. Finally, it consumes that item. So this is a more structured way of approach that precisely managing the resource usage and coordination. Yes.
For how for this one, even if it's pulled out of the queue, it still does form check to make sure that the variable.
Yes. Now, here, it simply concludes the lecture of the entire semester. What a long way. Any question? If not, so let's end right here. You can have more time on your homework 4. And for whoever is attending on the Zoom, thank you for coming.